Hello, everyone. My name is Manuela Girotto, and I am an assistant professor at Berkeley in the Department of Environmental Science and Policy Management. And my research group really investigates different aspects of the hydrological cycle. And we do so with the help of models and satellite observations, and also by developing techniques that aim at merging both of these streams. And these techniques are also known data assimilation. And in today's presentation, I will give an application of data assimilation for estimating profile soil moisture. So why do we care about profile soil moisture? Many reasons, but some of the key is that the profile soil moisture has an influence on weather and climate, and it's also really the link between the cycles of water, energy, and carbon. We depend on water for our economy, agricultural, industry, energy productions, and we do use it for recreational purposes. However, due to climate change and variability, this resource has become very precious. Think, for example, about hydroclimatic hazards such as droughts, flood, and landslides. So because of this, we really need to estimate profile soil moisture in a continuous way. And when I say continuous, it's really just continuous in space and time. So then we can provide decent high spatial and temporal resolution estimates of these pressure source, and therefore the profile soil moisture. When I talk about profile soil moisture, really mean in this presentation, soil moisture, groundwater, and terrestrial water storage, which is kind of like the integral of both of them. So how do we really observe these quantities, but in general, earth science or environmental science variables? So we do so again with satellite remote sensing, among others. And we'll be focused again in satellite remote sensing because they provide a unique way to observe different aspects of the environment. So it's a window view observations of the Earth from space. You can also access the regions that otherwise will not be accessible. So think about complex terrains like mountains or regions with conflicts. And again, they provide a global snapshot of reality at this specific time. And a lot of these agencies, and in here I'm just showing the US NASA Aerospace Agency, they provide free and open data. So you can see just on this image, but these are only, again, the NASA satellites. There are many more satellites out there from different agencies that are observing the Earth science mission. So again, there are a lot of them, but I think that none of them, well, we are not really doing a great job at using them comprehensively. And part of this is also related to some of the key disadvantages of remote sensing satellites from space. So some of them are related to the points that I will be talking today. And again, today I will be stressed on the fact that some of these observations do not provide continuous in space and time estimates of the specific variables that we are looking at. So then, for example, in here, I'm showing just one day of estimates of soil moisture. And you see that for the specific day, you have a lot of regions that are now sampled, and those are the white regions. Another key problem that, again, I'll be stressing today is that some of these satellites, specifically that satellite that I will, again, talk, it's a gravity mission that is meant to observe the terrestrial water storage. They have very coarse space and time resolution. So they come every month, and they temporal in that spatial resolution is about 300 kilometers. And then most importantly, some of these observations are, yes, observing some quantities of the environmental variable that we are looking at and we are interested, but maybe we are interested in other variables. So I'm giving a practical example here. So in the case, for example, of surface of soil moisture, what the satellite can see is really what happened at the surface. So the first few centimeters of soil moisture on the ground. But if you are interested in understanding how much water is available at the roots for agricultural purposes, for example, what you really would like to get is the root zone soil moistures. And that's kind of like below the surface, so you can't really directly see it. with satellite observation. So again, the key point here that I wanted to make is that satellite observations alone might not be sufficient to provide a continuous in space and time real estimate of the profile of soil moisture and the groundwater as we were hoping to get. So what we do is sometimes developing these techniques called data assimilation, which really in general can be applied to any general phenomenon. In my case, I will just be talking about profile soil moisture and groundwater or terrestrial water storage. And the key idea behind it is that we can either observe these phenomena or model these phenomena. So observations can be, again, satellite observation, but traditional in situ observation or airborne or drone observations. And we can model these phenomena. So if you think about profile soil moisture, we are usually talking about land surface model that really just in essence solve for energy and mass balance equations to provide estimate of, in this case, profile soil moisture and terrestrial water storage. What the data assimilation does is acknowledging that both of these two streams, so both observations and models, contain uncertainties and errors. And by recognizing that, what we do is use statistical estimates, Bayesian estimators, to merge these two streams together and provide optimal estimates of that phenomena of interest. So then we can provide that continuous in space and time high resolution of the variable of interest. So overcome essentially that pitfalls of both data streams and enhancing the benefits of both. So again, in the rest of the talk, I will provide an application of data assimilation for soil moisture profiles. So estimating soil moisture and groundwater by assimilating microwave observations and gravity observations. I'll start with the microwave observations. And this is because soil moisture, in a way, with respect to groundwater, is relatively easier to estimate because we already have dedicated missions in space, specifically from NASA and from the European Space Agency, that are dedicated to observe soil moisture. So what happened is that the radiometers that both of these missions have, it's on a L-band microwave band of the electromagnetic spectrums, and it receives signals, a microwave signal that is sensitive to profile soil moisture, and it does so at about 40 kilometer resolution. So again, this is great because you have this brightness temperature observation that is sensitive to soil moisture. The observations come every 2-3 days, and you have a decent spatial resolution. Again, if you're looking at global mapping of profile of soil moisture. The problem, as I was mentioning earlier, then that you have gaps in these observations. So you do have some in a specific day areas that are not sampled. But then again, most importantly, you're sampling really just this soil moisture at the surface. But oftentimes, what we really care about is the availability of soil moisture to the plants, for agricultural purposes. So how do we translate that? So to translate that, again, we develop a data assimilation technique where models and observations are brought together. The observations that I will show results of today are only from the European mission SMOS. And the model that we use is catchment and surface model, which is a model used by NASA to estimate, among others, also the profile of soil moisture and so on. This model has been coupled to a radiative transfer model by a colleague. So then we were able not only to estimate profile soil moisture, but also brightness temperature. And this is a critical step because now we can compare brightness temperature that is modeled and brightness temperature that is instead observed, and use this difference, so the model versus observed brightness temperature, to generate increments, so to adjust the model in soil moisture space. So essentially translating the brightness temperature to soil moisture states, and not only doing that, but also translating what happened at the surface to the root zone, taking advantage of the relationship that is determined essentially by the model. And by doing so, we are also distributing these increments spatially, so vertically and spatially. And a visual representation of what I just said is shown here, where you see differences in observed minus forecast brightness temperature from emissions map. And you see how these differences, for example, where you see warmer brightness temperature, you see that the model is essentially removing moisture because the observation is warmer with respect to the model. And by doing so, you're adjusting also other layers of soil moisture, so the root zone, and you're extending that in over space. So you have essentially continuous estimate of both surface soil moisture and root zone soil moisture in this case. Let's talk about gravity emission. So why are we talking about gravity emission? Well, we know that gravity is not constant over Earth, but it varies. So if you're in the mountains, you might have more mass and therefore the gravitational field is higher. But the gravity also changes over time. And these changes in gravity over time are associated to changes in water, changes in anomalies in water. And essentially this mission, which is called GRACE, and GRACE follow on, it's observing these anomalies of water over the entire globe on a monthly basis. So what we do is, again, using these observations that are great because they can see beyond the surface. So by essentially measuring the mass of water underneath the surface, you can see beyond the surface. So, and that's in contrast with what the soil moisture missions were seeing. It's great for global studies, and it has been used for ice melt, sea level rise, and so on. But for hydrological purposes, it's not so great because it only provides the mass of water, doesn't really tell me where the water is coming from, the groundwater, the soil moisture, the snow, and so on. And most importantly, they are very coarse in space and time. So observations come every month, and their spatial resolution is about 300 to 400 kilometers. So in a way, like the entire width of the state of California. In order to downscale that, again, we use data assimilation schemes, where similarly to what happened with the soil moisture, we use the same model. The observation now are the gravity observations. And we use a data assimilation scheme where the model essentially predicts that variable that is observed by GRACE. And then we use the relationships in the model to again downscale those observations from the gravity mission to a finer scale spatial and temporal resolution. So in a way, taking advantage of the model structures to refine the coarse resolution of GRACE, terrestrial water storage observation. So again, just as an example to illustrate this concept, you have that observation for GRACE. This is for the US, the difference of the two observations, and then data assimilation that is used to downscale, in this case vertically, from the surface, soil moisture, and groundwater, the observations of gravity. So in a way, essentially just taking advantage of the model structures, again, to refine the coarse spatial resolution from the gravity emissions to something that makes more sense for hydrological applications. And by doing so, we are also downscaling that integrated variable TWS into surface, root zone, and groundwater. To put these all together, so both the assimilation of soil moisture and gravity observation, this slide shows how well we're doing by doing so. So what you're looking at here are differences in model scale, where the model scale is measured with the correlation scale, where you see Whenever you see blue, it means that the assimilation on that specific variable. First column is the gravity. Second column is the soil moisture. Does bring improvement to 4 different components. And I'm looking at surface soil moisture, root zone soil moisture, gravity, and the combination of both, so the terrestrial water storage. So what you see is that you see mostly improvements in the groundwater and terrestrial water storage, of course, when you are assimilating those gravity large scale observation of TWS. Most of the improvements that are brought by the soil moisture mission happen in the surface and root zone. But when you bring them all together, you do maintain the benefits of the both. So the key point here is that the best estimates are obtained when you both assimilate soil moisture and GRACE observations. So to conclude, I hope that I convinced you that data assimilation is key to do a lot of things, among which to downscale those gravity observation, both vertically, horizontally, and temporally. The data assimilation of soil moisture can be seen as a way to filling in the gaps. The combination of both soil moisture and gravity emission will lead to better estimates of the hydrological cycle. And then again, most importantly, this data assimilation can be used to estimate a variable that is not directly seen by the satellite. So what are the remaining challenges and opportunities with data assimilation? This is really the key of my ongoing research. So then if you do have any more questions, I'll leave you with my email, and thank you for your attention.